Okay, all right, so let's introduce our last topic, and that would be AC power. In AC power will work again based on the principle of energy transfer and energy storage of the inductor and the capacitor. So let's see. Okay, power in AC circuits, what what is it, and why it's important. So when we studied resistors, power was simple. Whether it's DC or AC, resistors behave exactly the same way for both. V equals IR, Ohm's law. P equals VI, product of voltage and the current. For a resistor, it would be I square times R, or V square divided by R. For a inductor and a capacitor, it's just not quite as straightforward. Okay, inductors and capacitors are energy storage devices, so energy is constantly flowing in and out. That means if energy is flowing in and out, it means power is constantly being transferred in and out of a inductor and a capacitor. Oh, sorry. So power, energy is constantly transferred to and from inductor and capacitor. Okay, it's constantly flowing in and out. If it was an ideal component, ideal system, then there would be no power loss, right? Energy would flow into the inductor or into the capacitor and it flow out without any losses in power. So here's what happens in real life. Real life electrical power is transmitted over very long distances, right? You all have seen long distance transmission lines that look like this. Now, at the consumer's end, we have electric machines. In a residential environment, the biggest electric machine or biggest electrical appliance would be your washer, dryer, HVAC unit, and perhaps your refrigerator. Even your refrigerator would not have like anything similar to an industrial customer, right? These are the biggest appliances in a residential environment, right? Let's take a washer or an HVAC unit, for example. It has a motor. The motor spins. The motor has a coil inside it. The coil, electrically speaking, is nothing but an inductor. It's a current carrying wire that is wound in a spiral shape. So electrically speaking, it is nothing but an inductor. So a residential environment will have an inductor inside a washer, dryer, HVAC unit, a refrigerator, anything that has a spinning motor that as a spinning motor has a coil. That means it has inductance. And what does an inductance have? Inductance has reactance. It stores energy in a magnetic field. So when an inductor stores energy in the magnetic field, in the reactance, the power associated with reactance is known as reactive power. Reactive power. Now, this reactive power does not do any real work. When I say real, does not mean imaginary or real. When I say real work, in a sense, it does not do any work of converting the electrical energy into useful mechanical energy. Okay, it is simply associated with the reactance. It is used to store energy in the magnetic field. Okay, this reactive power is real. It has a physical basis in real life. Okay, similar to how reactance is. Reactance, we use the imaginary number. So oftentimes you might read the words imaginary reactance. but there is nothing imaginary about it. It is real. It has a physical basis in real life. Okay. So similarly, reactive power is represented with the imaginary number, but it is real. It has a physical basis in real life. Now, what does this have to do with what we are going to study in this chapter? Well, this reactive power, as I stated, does not do any work of converting the electrical energy to useful mechanical energy. Yet, the power supply company, the utility company, still has to send the voltage, the current, the energy that is associated with this reactive power. So for instance, if you have a washer connected at your end, at the consumer's end, that washer has an electric motor inside it. That electric motor has a coil, which is an inductance. It has a magnetic field. When you first turn it on, that washer requires, that motor inside the washer requires electrical power. That electrical power is split in two parts. Mathematically, we can separate it into two parts. We can say that there is a real component to that power, and then there is a reactive component to that power. So real power and reactive power is the total power that is required for that appliance. Now, if it's an inductor, what happens? It receives the energy from the utility company, right? But if it's an inductor, what happens? Energy flows into the inductor and then flows out. When it flows out, where does that energy go? It goes back to the utility company. Okay, so if you have a utility company, it is sending energy to the consumers. Consumers are of two kinds, residential versus industrial. Residential consumers, the biggest appliances are washers, dryers, HVAC units, refrigerators, perhaps ceiling fans. Compared to an industrial customer, these are very, very small. They are very, very tiny. Okay, so the inductance level of these appliances in a residential area is very small. It's very tiny. The effect that these inductances have on the utility company is very small, is negligible. Okay, also think about the fact, if you have a washer dryer in residence, how many times are you going to use it in a day? Maybe once a week, twice a week. If it's a big household, maybe 3 times a week. HVAC units, they turn on, they turn off, they turn on, they turn off, but it's not going 24/7. And even if it is very, very small. Okay, it's not that big a load. Compared to an industrial customer, where industrial customers have huge inductive loads, have big electric machines that run for 8, 9, 10 hours a day, sometimes even 24 hours a day, 7 days a week. There are some equipment that are always running. For instance, we have cryogenic generators, not cryogenic pumps that run 24/7. Whether the machine is in use or not, that pump is always running. Okay, it's an electric pump that has an electric coil and is always running 24/7. So industrial customers have different needs. They have huge, big electric machines compared to residential customers. And these inductive loads have much higher level of inductance compared to residential customers. Inductors and capacitors, again, we talked about how they have reactive power because the power associated is with the reactance. So the power associated with an inductor and a capacitor is termed as reactive power. Remember, ideal capacitors and ideal inductors do not have any real power. When I say real power, I'm talking in terms of the resistive power. Okay, so again, reactive power, like reactance, is mathematically represented with the imaginary number J. So imaginary number J is used to represent it, but there is nothing imaginary about it. It is real. It has a physical basis in real life. Only mathematically speaking, we say it is imaginary reactive power, like imaginary reactance. Okay. Only energy storage elements like inductors and capacitors have reactance. So reactive power is associated only with inductors and capacitors. Okay. So reactive power is associated with only inductors and capacitors, not with resistors. And the thing with this is that if it's DC, then the energy flows in one direction. It's AC, then it flows in both directions. So if you are a utility company and you are serving an industrial customer that has huge electric machines, you are sending voltages and currents over very long distances. It travels back and forth. Remember the previous chapter where we talked about how a AC voltage or current will constantly flow in and out of a inductor or capacitor. You all with me so far? Now imagine if that circuit is not localized, meaning your source and your load, which is the inductive machine, is hundreds of miles apart. What happens then? Then the voltage or current is being transmitted over very long distances, meaning in the positive half cycle, energy flows from the utility company all the way to the industrial customer. Negative half cycle, it flows all the way back out, back to the utility company. This is being transmitted over long distances needlessly because it is not doing any real work. It is simply associated with the reactance. It is not doing any useful mechanical work. So it is needless transmission. And every time voltage or current flows through your wires, there is power loss. A wire doesn't matter how good of a material is, has resistance. That resistance is equal to rho L over A. Rho is the resistivity of the material. L is the length of that wire. If this length is hundreds of miles, doesn't matter how large the area is basically the cross section of this wire. If this L is hundreds of miles long, the resistance is large, the power loss that occurs is I squared times R. This again goes back to chapter 1, where I said if you want to transmit electrical power or long distances, you want higher voltage and lower current. Because the higher the current, then your power losses are also higher. That's why most of the world transmits power in 220 volts, not 120. So power losses that occur in the system are kept much lower. Anyway, coming back here. Utility company, power goes to the customer sends it back, right? Every cycle is exchanging power. And the frequency of transmission is 60 hertz, at least 60 hertz. I mean, 60 times in 1 second, power flows into the industrial customer and comes back out, back and forth, back and forth. Every time you transfer this, power is being lost. The total power that is being sent, utility company has to send the real power plus the reactive. The machines don't distinguish between real and reactive. Okay, it is all one single voltage, one single current. Okay, one single voltage and current. The machine itself is going to use some of it for reactive purposes, the other for real purposes. Does that make sense? So the costs associated with sending this much power and back and forth is insane. It's prohibitive, right? And so we do not want to needlessly send this much power back and forth all the time. So industrial customers are paying not only for the real portion, but they're also paying for the reactive portion. Residential customers, not so much. They're insignificant compared to real. So what do we do about this? Well, fortunately, we have the capacitor. And as we saw in the previous chapter, if you have a capacitor in the system, when the energy flows out of the inductor, it goes into the capacitor. And so the concept here is this. When you first flip the switch on, you have a brand new machine, let's say. First flip the switch on, that huge inductor requires certain amount of power. Utility company will send that real and reactive power to that inductive machine. The inductor receives the power. Next half cycle, the inductive machine sends the power out. But instead of going all the way back to the utility company, if we place a capacitor in the front of the machine locally, then the power, instead of going all the way back to the utility company, goes into the capacitor. So the next half cycle, when the inductor requires that reactive power, that energy comes not from the utility company, but it comes from the local capacitor. Make sense? So instead of going back hundreds of miles to the utility company, it's only going, I don't know, a few yards. And this process is known as power factor correction. So we'll talk about that a little bit more later. But you put a capacitor locally in front of the system, so the power goes out of the inductor and into the capacitor, and then when power goes out of the capacitor, it goes into the inductor or into your electric machine. So now power is localized. So when you first flip the switch on, there is a transient portion where there's a huge amount of power coming from the utility company all the way into the industrial customer. Once it reaches steady state, meaning the inductive portion of the machine reaches full charge, power flows out, goes into the capacitor, and from that point on, the energy transfer that takes place locally between the inductor and the capacitor. And so from the next, once the system reaches steady state, the utility company does not have to send all of that power all at once again. And so the power requirement is now low. Let's take a pause while you think on all of that. Let me know if you have any questions. Did all of that make sense? It's a tricky, hard concept to get. So I want to make sure everyone understands that before we go to the equations. Yes. So the question being asked is, how long does the process take of charging up that machine? The answer would be, it depends on the size of the machine, but it shouldn't take more than a few seconds or a few minutes. Again, depending on how complex that machine is. If it's something small, like, one motor of an appliance or something, then it's pretty quick. Yeah, fraction of a second, exactly. And with a huge machine that is like running inside a huge warehouse, it's going to take a very long time. Well, very long time, again, it's relative. It's a few minutes, not like hours or days. But continuing on at that point, if you have let's say an industrial factory and you have like tens of these machines running, okay? If the power goes out, then the industrial customer cannot turn on all the machines all at once, because the utility company transmission infrastructure is not set up to handle that much power. It's not set up to handle that much current. So when the power goes out in an industrial area, the industrial customer has to work with the utility company to have a staggered turn on. That is true on Cal Poly's campus also. All universities have big electric machines running all at the same time. And so there are people who are in charge of these departments, and they work with the utility company to have a staggered turn on. You call the utility company, and the utility company says, okay, what is your requirement right now? I will send you this much power. You turn on one machine, then one machine reaches steady state, then you turn on the second one, because otherwise the system cannot keep up. Okay, and that technically is defined as the power factor. So let's go into the equations. So total AC power is given by the equation S is equal to P plus JQ. Okay, total AC power is referred to as total complex power because we use complex numbers. We use complex numbers to write our equations. So P still says the same. It is our average power, or we also say it's a real power because it's the real portion of the total complex power S. The new terms are your reactive power. And reactive power has different units. It is known as volt ampere reactive. Volt ampere reactive. Total complex power S is termed as volt ampere. And this, of course, is simply watts. Okay, watt. It is a complex quantity, meaning S has magnitude and it has phase angle, theta. Okay, and again, similar to all complex numbers or the charts that we've seen so far, this is your real axis, this is your imaginary axis. S can be plotted like this. This would be Q, this would be P on the real portion. This would be magnitude of S. This would be the angle theta. That is known as the power angle. Power angle. Power angle is the same as the impedance angle for a component because it is the difference between the voltage and the current phases. Okay, difference between the voltage and current. So again, AC power is noted by the use of complex numbers, noted by S. S is the total complex power. Unit is volt ampere. And S is equal to P plus JQ, or P plus Q, but we use the imaginary number to make our math easier. This is P plus JQ. P is our standard power associated with the resistance. Q is the reactive power associated with inductor or capacitor, and it has units of volt ampere reactive, VAR. VAR. Let's take a pause before I go to the next slide. Yes. Where? Oh, real axis and imaginary axis. Yeah. So here's how we handle this mathematically. ZL is always positive. Right? Impedance of a inductor is always positive because it is always pointing up. Theta V minus theta I is always positive 90. ZC, on the other hand, is always negative. It's always pointing down because theta V minus theta I is always equal to minus 90. Right? Energy flows in a positive half cycle, energy flows into the inductor, but out of the capacitor. Exactly the same functioning, but opposite in phase. Hence, if you plot QL, QL will always be positive in the sense that it is always pointing up. And QC is always negative because it is always pointing down. And when I say pointing up and pointing down, this is the positive imaginary axis, and this is the negative imaginary axis. Okay. So if we use, this is the real axis, and this is the imaginary axis. This is where we would plot our real power P in watts. And this is where we plot our imaginary Q. Okay. So if you have a system, that has inductors or capacitors, well, inductors, capacitors, and resistors, and you plot the power for all three components on the same graph, well, P would be lying flat on the x-axis because it's real power associated with the resistance. It does not have any angle. Okay. Whereas QL is always positive, plus 90, and QC is always negative, pointing down. Okay. So this is pointing up, this is pointing down. And when you join P and QC or QL together, you get what is known as the power triangle. Power triangle. And power triangle for inductor always looks like this. Power triangle for a capacitor will always look like this. Well, that is if you have a resistor in the system. Okay, if it's just the inductor, power triangle would simply be an arrow like this, because it would not have any real component. P would be equal to 0. So PL would be equal to 0. It would simply be QL and QC. That's it. When you combine it with a resistor, then you get a power triangle. This is also the magnitude of S. Magnitude of S is given by the product of the voltage and current, VRMS times IRMS. The equations are on the next page. Let's take a pause. Let me know if you have any questions about the power triangle. Any questions at all? The equations are very similar to what we did for chapter 5, complex impedances. We use the same imaginary numbers, okay, the quantities are different. So it can get confusing at times. But again, remember that you're simply using complex numbers to make the math less complex. Any questions? Okay, here are some of the other equations. So complex power S has magnitude and phase angle. So S has magnitude of S and phase angle theta. Magnitude of S is also defined as apparent power and given by the product of the voltage and current, Vrms times Irms. It is also given by this equation, which is half VI asterisk. Half VI asterisk. It's a product of voltage and current, but because of complex numbers, the equation comes out to be half VI asterisk. I will explain what that asterisk stands for. But before I do that, I want to go over the other equations. If you look at these equations, they have a very similar structure to P is equal to I squared times R. So here, let me write it inside. Chapter 1, power is the product of voltage and current, V times I. So we have the equation for S, which is V times I asterisk. In terms of the resistors, V equals I R, Ohm's law. So we can write P equals I squared times R, or P equals V squared over R. Everyone remember these equations, right? I squared times R, V squared over R. Now look at these equations. Okay, exactly the same structure. But if you're AC, what do we say? We want to define an average value for AC. An average value, of course, is the RMS value. So mathematically, when we write out the expressions for P and Q, we use the RMS values for the current and for the voltage. Okay, so for an AC system, the average power associated with the resistor in that AC system is I RMS square times R, or V RMS square over R. Okay, the structure of the equation does not change. Only the quantities you are using changes. And when it comes times for capacitor or inductor, you're dealing with either XL or XC, reactance of the inductor, reactance of the capacitor. As a reminder again, ZL is J times XL, J times omega L, J times 2 pi FL, omega times L. ZC is 1 over JXC. And XC is 1 over omega times C, or you could write 1 over J 2 pi FC. XL and XC are simply 2 pi FL and 1 over 2 pi FC. It's without the J. Okay, it's without the J. So Q, reactive power for inductor, would be I square RMS times XL. QC would be I square RMS times XC. Same thing for voltage, VRMS square divided by XL or VRMS square divided by XC. Here, the voltage and current are phasors. Okay, they are vector quantities. So you have to take the phase angle into account. They are not RMS values. Note that they are not RMS values. They are phasors, they're vector quantities. It is the magnitude of the voltage and the phase angle for both voltage and current. Remember, S is a complex quantity. Anytime you see S, it has a real portion and an imaginary portion. The real portion is P, imaginary portion is Q. Those are the rectangular coordinates. If you convert it into polar coordinates, you have magnitude of S, which is given by this equation, or you have the phase angle for S, which is given by theta V minus theta I. And theta V minus theta I is the power angle. It's also the impedance angle. It gives you the power angle theta. If you take cosine of the theta, you get what is known as the power factor, PF. And cosine of the power angle, because we want to describe the requirement of Q, trigonometric identity, cosine theta from the right angle triangle, we want to describe the requirement for Q. Remember, the goal is that the utility company, the source, should not be supplying the reactive power for the inductor beyond steady state. Right? When the switch first flips on, source sends all the reactive power that is required, but after it reaches steady state, the capacitor should be supplying that reactive power. So what happens? We have this, right? Let's say you have a system that requires this much amount of real power P and this much amount of reactive power QL. So this is the amount of total complex power that your utility company has to send from the source. If you put a capacitor in front, the capacitor now supplies this much reactive power, which is in the opposite direction. So your actual power requirement has now dropped. Your angle is now reduced. Does that make sense? Does that diagram make sense? You had the inductor that required a certain amount of power, right? So your utility company or your source is supplying P plus QL, but now you place a capacitor in front, it charges full, and then from the second half cycle, or at least from steady state onwards, a huge portion of QL is supplied from the capacitor, meaning QC. Make sense? In ideal conditions, you would want QL equals to QC, which is never possible. So if you look at this equation, what do we see? Cosine of theta describes how much reactive power is required by that system, because you want to make it as small as possible. The ideal goal would be to get theta equal to 0. Cosine of 0 would be 1, or in terms of percentage, we say it's 100%. Power factor is a term that we use to describe the reactive power requirement for a system. We want that angle to be as small as possible It's not possible to get 0 because, the speeds of the machine vary, how much the machine is utilized varies, the overall load of a system of a customer always varies. It's never constant, it's never fixed. Okay. So the goal is to get it as close to 0 as possible. So power factor is basically describing the power requirement, the reactive power requirement of a customer, of a system. And it's given by the cosine of the phase angle. Cosine of the power angle. We want that power angle to be as small as possible. Power factor, cosine of theta, is described in terms of percentage. The highest value would be cosine of 0, which is 1, which is 100%. For all other values, it would be 0.99, 0.98. So it would be 98%, 99%, or 90%. If it's below a certain level, the utility company will not supply power. It will say your power factor is below 90%. You need to bring it above 90%. Otherwise, I'm not going to send you any power. Okay. Let me stop right here because that's the end of our time. And then the only thing left on the docket is going through the 2 examples, which I will do on Wednesday. So we'll end class here today. There's a lot of equations and a lot of theory to get through. So review this, as at your earliest convenience, and then I'm available to answer any questions if you have so. But for now, we'll end class here today.